So I'm going to be talking about small I/O on distributed file systems. A few years ago, when I was at Red Hat, I worked on cluster, and I did a project called storage tiering. And in the beginning, the performance was not that good. Performance was not that good. Can you hear me now? The performance was not that good because of small I/Os, it turned out. And it took a long time to figure out why that was. Last year, I went to FAST, and the keynote speaker, Garth Gibson, mentioned that he had been doing work on metadata optimization for distributed file systems. I investigated, and this turned out to be exactly what I needed. And in fact, there was a very large set of work in the academic world that was very relevant to the problem. So, at my new company, I was fortunately funded and allowed to dig deeper into this. And this talk is the result, along with some open source code, which I'm posting. So I'm going to first talk about the targeted use cases. I'm not going after all file system workloads, but a very specific subset of them. I'll talk about the problem. I'll talk about existing strategies that you'll find in Ceph and Gluster. And then talk about the work that came out of academia. And then I'll show this implementation that came out of the universities, give a demo, and most importantly, show you the workflow, because what I am aiming this for is for analytic workloads, not all file systems, but analytics. And this is a very specific case where you have many clients performing analysis in parallel, but they're doing so in a cooperative manner. What they're basically doing is they're taking a chunk of the file system, doing some work on it, and producing some result. They don't tend to work with each other. They don't tend to step on one client does not step on another client's files. So there are weak consistency needs for this case. And we'll call those cooperative clients. Why are we using distributed file systems for analytics is basically because domain experts don't want to learn something that is exotic. They're used to file systems. So if you say, well, why are you using file systems? It's because they want to use file systems. Granted, you could invent something faster. But they don't need a enterprise-grade file system. So exotic features are probably not needed. It doesn't even need to store data, because your analytic data is probably stored in perhaps S3 or somewhere else, and it's pulled in from that data lake. So it is only for analytics. That's the use case I'm targeting here. So the small transfer problem is basically when you have a round trip over the network. It tends to dominate all other performance. This is because of network overhead. It's because of queuing. These all add up. And they're basically baked into how file systems work, because when you access a file, you need to check every component of the directory to make sure it exists, and you have permissions to do it. That's the path traversal problem. And it shows up in other cases when you have many files in a directory. That's actually pretty common. Any stats or negative lookups, those are all small transfers. And analytical applications, it's very common to have small files that you're working on. Current one that we're seeing more and more of is AI learning samples. They tend to be very small. So let's say you're teaching how to do something. There might be lots of small files, and each one represents a sample. And also typically when you have lots of threads running doing these analytics, the thread will create a file, a checkpoint, saying, I'm done. So it creates the checkpoint, and that's a create, and that goes to the server, and that's another example. So these come up all over the place. Well, strategies that we have had for a long time now are First, you can split the data from the metadata and have a metadata server. You can have multiple metadata servers, and this makes the metadata not block data transfers, but you still have to go over the network to reach the server. You still have that overhead, and you still have serialization for if there's two clients accessing the same bit of metadata. Popular directories can become hotspots, and these metadata servers, they don't auto-scale. So you might have a fixed partition of your namespace. Client-side caching is another very popular technique. It was mentioned earlier that the MD cache translator in Gluster uses this to nice effect. Here's something I did at SNIA a few years ago with the results of my experiment with cluster tiering. You can see the red on the top graph is the throughput I got when I enabled client-side caching. It's great if your cache is preloaded, if you've already loaded it. But you still have to synchronize with the server on any mutations. If you change some metadata, you'd have to go to that server. And of course, it takes up client resources. But it does work when it works. So here's the corpus of work from Carnegie Mellon. This is actually done by Garth Gibson. So I'm going to go through these briefly, and then I'll show you the new stuff. They basically landed on the last one, which is called ΔFS. And then in the last couple of years, they've been applying it to different high-performance computing applications. They started with something called tableFS in 2013. This was done for local file systems, not distributed file systems. And the idea here was to take modern key-value DB techniques to store their metadata, basically an LSM. And they showed that this was faster than how ButterFS and XFS stores their metadata. They showed it was much faster. Why would an LSM be faster? Well, there's three contributing factors why it was faster. The first is writes were very quick. When you do any mutation, an insert, a delete, any change, it goes to an in-memory mem table and then persisted to a write-ahead log. So it's just a log, and that's pretty fast, so it's great for writes. And the second reason is that this mem table gets, when it reaches a certain size, it's passed down to the levels below where it's later compacted. And these data structures below are called SSTs, or sorted string tables. But it turns out they're really easy to work with. They're really easy objects for a computer to deal with. They're immutable. You can't overwrite them. So a lot of issues with defragmentation and so on go away. And then the third contributing factor why they got such great results was that the keys were very clever. They put the directories and the file names into the key. So for example, if you do a readdir, you can get all the files all at once from for that directory, because they're all adjacent to each other. You can actually just read them out in a batch. The next in their next publication was IndexFS, and what they did here was they took the tableFS idea and they extended it to distributed storage. And they attacked the issues that I mentioned earlier with client-side caching. Basically, the issue with client-side caching is it's okay until you do a mutation, but when you have a mutation, you have to do what they call in Gluster an upcall. But what you see elsewhere in literature, do an invalidation storm, which means you have to go to every client and invalidate what was in the cache. What they did in this paper was to get around that by giving leases to path name components. So when you go to a file, every path name component is granted a lease. You don't have to store it per client. It only keeps the largest lease. And if someone wants to do a mutation on any of those components, it has to wait until the lease expires. Now, you still have to go to the server to get these leases, and you still have to go to the server for mutations. But it made life a little bit better. Another of the innovations in this paper was what they called bulk creates. So here the idea is that you can create many files. You create them locally, and then you send them to the server all at once. So I create 100 files locally, and then I send them to the server all in a batch or bulk insert. But what if somebody else is modifying that directory at the same time as me? Well, they invented a variant of the makedir command with what they call the localize flag. It works, but of course it deviates from Posix, and that's not good. There were some other innovations here which I probably don't have time to do, which are IndexFS was a great paper. The next in their series was BatchFS. And what they tried to do was address the client synchronization problems that I mentioned earlier with the leasing and the mutations. And the idea here was to take the metadata server and actually move it to the client. So now there's a library. A library that you run on the application, on the client, is the metadata server. And what about clients? How do other people know about those changes? Well, the clients work on a snapshot of the file system. So every client will take a snapshot of the file system, work on it locally, and then when they're finished with their work, they'll publish that snapshot to a server. They only do it when it's necessary. Then they have an auxiliary server in the scheme which will merge those snapshots all together with a global master image. This is nice because it scales very well with the number of clients, the MDF servers, but, and the performance was extremely good, but the merging is really hard. What if the client's untrusted? Here's an example of how you can do snapshots with an LSM tree that's very elegant, and it just depicts again why the LSM tree is a nice object. Let's say you have made those changes in blue. You can dump them. And dumping means you iterate over all these levels, looking for version numbers that match your snapshot level. Those can go into an object. So now, if I want to restore that snapshot into a different LSM tree, it's simple. All I have to do is take that object and rename it. When I rename that name of that object to be a level 0 entry in the destination LSM tree, just a rename operation is all it is. That is brilliant. Ceph doesn't allow you to rename objects as far as I can tell. So in my implementation that I tweaked from the university, I copy it. So that's something to talk about offline. So finally, they reached tableFS, which the merge problem was very serious. That was sort of the most difficult issue. In tableFS, they say, well, these are cooperating clients. That's our use case. So we have cooperating clients. They do not touch each other's work. And so we're going to leave this to the application to define how to merge snapshots. And in practice, if each is working on their own set of files or their own directory, for analytics, they're not going to step on each other's toes. That's the use case we're interested in. So the workflow is like this. We have two clients. One makes a snapshot, and the other makes a snapshot. Those get pushed into, for example, Ceph, but it could be anything. It could be EFS. And another auxiliary server will pick up those two snapshots and merge them together and create a new snapshot. So the file system is nothing more than a set of snapshots. So now you're left with the problem is I have to manage the set of snapshots. And that's the workflow issue, which I'm interested in. So I've made a fork of, this is an open source event here, Vault. I've made a fork of tableFS, and I've started to make some improvements on it. And this talk is part of the documentation. I made some minor fixes, and I've also containerized it. The advantage to containerizing it, I'll show in a moment. So working with code from academia has been an interesting experience. It brought back memories for me from the 90s. You basically have a mix of different research projects that have been done over the years. And there's some other bugs here. Okay. I'm going to skip the demo, but what the demo shows are two containers where you can each creates a set of files, and those get piped to another container which merges that files, and it's all using Snapshot. How do you? So we don't want to change Posix because one of our use cases, we basically want the user not to have to change their applications. So how do you express these snapshots? The answer is that you set these environment variables. One is ∆fs input, which is a list of the snapshots that you're going to import. And ∆fs output is the name of the snapshot you're going to export. Okay, so the next question, when are these snapshots created? The answer is when the application exits. So the workflow is you have to set those two environment variables, and you have to modify your application to use lib-∆fs to change the file API calls. When the application exits, the snapshot's created. Or you can use my container, which puts ∆fs into a pod, and you can also put your application unmodified into that pod. And now when the pod exits, when the container exits, this is all very nicely done with YAML scripts and so on, the snapshot's created. Here's some links. I'll post some stuff later this week after scrubbing it to make sure there's nothing from my company on it. And in conclusion, so I set out to see how realistic these ideas were. I found them to be very exciting when I read them last summer, and I wanted to see how practical they were in the real world. They work when you're using cooperative clients, and I believe that does satisfy a large number of use cases. And two, when new workflows are acceptable, that is, you have to grok how these snapshots are imported and exported between instances of these applications. That's a little bit harder, and that's basically teaching people. Code is unfortunately still a proof of concept because it's from academia, and will take a lot of iterative steps to bring it up to date. Again, that's part of open source. I believe we need to, so I'm going to stop right there, actually, since I'll take any questions, but that's it for me.
Just sort of an idea or a suggestion about the whole merging problem. Obviously, when you first started presenting that, it was clear that this is like Git, everything is a merge conflict. Since you are working in a cooperative system where everyone is working on separate data sets or directories or some unit of work that doesn't collide, could you implement some kind of checkout mechanism where someone grabs a lock on a section of namespace, a directory or whatever, guarantees anyone goes after it has to block until the first guy frees it up, then the merge becomes inconsequential because there's nothing ever to merge because you guarantee only one guy could possibly have a namespace to work with. It sort of makes the merge problem not a big deal. Is that something anyone considered? A halfway decent idea?
The merge problem comes up when two clients are stepping on each other's toes, but as long as they're not stepping on each other's toes, I think it just works in general. So in a lot of cases, it really doesn't come up that you have conflicts. That said, maybe your idea is something we could explore offline. I'd like to hear more.
Okay.
Oh, wait. Thank you.
Carlos Malzahn, UC Santa Cruz. So you mentioned Ceph a number of times, but I couldn't quite figure out why. And then the other thing is, are you aware of the Codele paper that we had published? Because we actually sort of tried to do the same thing using some built-in mechanisms in the metadata server in Ceph.
Can you repeat the first question?
The first question is why you mentioned Ceph a number of times, but that was sort of out of context. I don't know exactly.
Oh.
And then the second one
Got
was,
it.
are you aware of the Codele paper?
Got it. Okay. Okay. Real quick. Second question. I saw on the a guy at the FAST conference last year. He might have worked for you. Same group, maybe. I'll definitely have to check that out. First question, Ceph. Actually, these run over any object-based system. I'm using Ceph for convenience because it's open source. But you could run it over EFS. You could run it over anything. And that's one of the cool things about it. There's no integration with the lower level. I like that part of it. Still gets better performance, though, with that overhead.